Hello, thank you for listening to this presentation. The paper I am going to present is Interactive Painting Volumetric Cloud Scenes with Simple Sketches Based on Deep Learning. My name is Lida Huang from the Department of Computer and Systems Sciences, Stockholm University. I am the first author of the paper. Volumetric clouds frequently appear in computer graphics and visual effects scenarios. However, synthesizing realistic clouds is a complex and demanding task, as clouds are characterized by random shapes, complex scattering, and turbulent appearances. Existing graphic design and video production generally use two approaches to obtain volumetric cloud scenes. First, using two-dimensional graphic applications like Adobe Photoshop, whereby the user creates a stamp brush and then defines a transparent cloud image. The other approach is creating three-dimensional physical simulations via some 3D software. For example, Houdini, Unreal Engine 4 and Blender can generate natural clouds by applying dynamic parameters, including turbulent noises, air velocity, and lighting. However, these two approaches require skillful techniques in computer graphics. The user has to test trivial parameters to avoid fake goofs, making creating a realistic cloud sky challenging and time-consuming, especially three-dimensional physical simulations. Additionally, physical simulations are usually dissipative for GPU implementation. In recent years, artists have used deep learning to create digital graphics. For example, Pix2Pix and SketchyGun synthesize translated photos from label maps, edge maps, and stylized images. But volumetric cloud scene was not involved in these two methods. GAU-GUN can transfer simple lines to various landscapes, but it contains a large semantic recognition network requiring vast calculations. Adapting GAU-GUN to synthesize high-fidelity high-resolution graphics can challenge computer memory. The output of GUNs is heavily dependent on training data. And so synthesizing volumetric clouds in fine detail requires an extensive high-resolution dataset. To the best of our knowledge, the only large-scale cloud dataset is SwimZeg, which only has a resolution of 600 by 600 pixels. There are currently no high-resolution volumetric cloud datasets for training GUNs. Furthermore, the aforementioned previous deep learning methods cannot reflect fine details from input to output nor conduct delicate graphical editing via sketches. For example, this figure shows an input with a sketchy letter at the right and the output generated by GAU-GUN at the left. Apparently, GAU-GUN is not feasible to precisely control the figure details. The input and the output are not aligned very well. Moreover, volumetric clouds in particle form differ from tangible objects in image patterns, example, wispy cloud boundaries, and cloud density. These features are non-intuitive and difficult to describe. To resolve this, we treat the sketch inputs as approximate contours of clouds so that the system can generate various boundaries, densities, and shapes utilizing detail refinement synthesizers. Our system synthesizes clouds based on simple user sketches and supervises realism automatically based on conditional generative adversarial networks. It includes three major synthesizers, facilitating editing of the fine details of volumetric clouds. The system contains a volumetric cloud database with a resolution 1024 by 1024 pixels and an additional alpha channel, which involves 2000 pairs of segmented cloud picture pairings and corresponding sketches. Thus, it is sufficient to synthesize the detailed characteristics of clouds with the alpha channel, including features such as density distribution, silverlining feature, and light flux. This system includes three synthesizers based on CGUN, a volumetric cloud generator, a cloud edge refinement generator, and an eraser synthesizer. In the interface, the background function has a palette to customize the colors in the cloud and the sky. The default background color is light blue. The draw function corresponds to the cloud generator, which has a brush for drawing on canvas. The user can draw arbitrary strokes on the canvas on a new layer. Clicking Convert can convert the sketch to a cloud after selecting a layer. Based on the stroke input, the trained cloud generator produces genuine volumetric clouds. The user may then choose to reverse the synthesis and repaint the sketch, resume the synthesis, or erase parts of the cloud and fix the erased portion by running the eraser synthesizer. The blur function corresponds to the cloud edge refinement generator, and has a blur brush that can blur certain parts of the strokes, creating a feather edge to the clouds. The erase function can erase the drawn strokes or a specified part of the generated clouds, and restore the rough edges left after the erasure. The layers contain multiple cloud outputs displayed by overlaying the canvas. The layers can be used to record the editing steps. We established a dataset with 2000 high-resolution volumetric cloud images. The images were collected from Flickr via Flickr API and resized to 1024 by 1024 pixels. Then we employed Cloud Segnet to segment the fuzzy borders of the clouds from the image backgrounds, and generated the edge maps of the clouds. Then, we translated the edge maps to the sketch paired patches using the interpolation of SketchRun on the edge maps. The paired data for training the edge refinement generator detected edge hardness, i.e., blurriness, according to the gradient amplitude and threshold of the map. To train the eraser synthesizer, parts of the edges of the clouds were removed randomly and paired with the original image. The system approach applied conditional generative adversarial networks, comprising two deep networks, a generator G and a discriminator D. The adversarial networks were trained together, the generator G to map the prior distribution Z and the input condition C, namely, sketches, to a desired output G, C, Z, and the discriminator D to learn the loss between the real pairwise X and the generated patches G, C, Z. The loss for the discriminator was given as log likelihood for two classes as loss D, D, G, equals the expectation of C, X log D, C, X, plus the expectation of C, Z log 1 minus D, C, G, C, Z. In turn, the generator G was trained to fool the discriminator D by maximizing the discriminative results of the classifier to 1, loss G, D, G, equals the expectation of C, Z log D, G, CZ. Prior research concluded that adding an L1 or L2 loss term to a small weight could enhance the quality and diversity of guns. The reason is that the outputs generated from an L1 distance are slightly crisper than from an L2 distance. Thus, we incorporate an L1 distance, loss L1 for G equals the expectation of C, X, Z bracket the L1 distance between X and G, C, Z. Therefore, our final loss function is loss, D, G, equals arg minimum G maximum D loss D, D, G, plus lambda multiples the loss L1 G. We performed random image cropping, random scaling and flipping to the image pairs to augment the data. We built UNet as the generator architecture to maintain low-level information across networks. Additionally, we added noise to the bottleneck of the UNet to encourage greater diversity and stability. We used ReLU in the 2D convolutional layers in the generators and set the numbers of the feature channels as 64, 128, 256, and 512. The discriminator used convolutional layers with leaky ReLU. The networks were trained based on the TensorFlow network and the Atom Optimizer. The Atom Optimizer was applied with no batch normalization and an initial learning rate of 10:4. Noise input was added in the generator, and a stochastic gradient with a mini-batch size of 20 was adopted in the network. To train the cloud generator, the train set included 1,600 image pairs, while the test set included 800 image pairs. The networks of the eraser synthesizer and the edge refinement synthesizer have 600 image pairs. All the synthesizers were trained with 150 epochs and tested on an NVIDIA A100, memory 40 GB. Images of two resolutions, 1024 by 1024 pixels and 512 by 512 pixels, were trained and fresh at inception distance was employed to measure the quality of the test results. The test result reveals that the three synthesizers successfully generated convincing volumetric clouds. The nearest neighbors corresponding to the ground truth were visually distinct, suggesting that the networks do not simply memorize training data, but also obtain diversity. The three synthesizers obtained FID scores from 8.473 to 19.504, while the cloud generator obtained the lowest FID score. It indicates that the sketch-to-cloud networks had the best performance. The total computational time for synthesizing during the test was under 0.2 s. It demonstrates that the system enabled the user to interactively and robustly edit and preview the cloud scene in real time. We then implemented a comparison experiment based on the system on an NVIDIA Titan V, memory 12 GB. To evaluate the graphical quality of the system, we compared the results obtained with our synthesizer to previously developed cloud simulation methods. 5 figures from the latest representative papers on volumetric cloud synthesizing and rendering methods were selected as the generated cloud samples. Then, we sketched the coarse silhouettes accordingly to the given samples, then input them into our synthesizers. The figure reveals that our method replicated plausible clouds based on the results obtained and easily created volumetric clouds of defined shapes. Compared to A, B, D, and E, our clouds have more details in the fuzzy boundary, shading, and scattering. In C, the cloud was created using deep learning rendering, thus achieving a better volumetric visual effect than ours. However, our clouds displayed volumetric features with a more straightforward image mode. Our method introduced a straightforward and efficient cloud sketching accessible to both novices and experts, lowering the professional requirements for creating natural clouds. Next, the system usability was evaluated by a user study with 5 participants experienced in drawing. The participants were asked to create the shapes they wanted by sketching via the 3 synthesizers of the system. In the end, the participants were asked 3 questions about the usability of the system. The result indicates that the participants can conveniently design artistic volumetric cloud scenes using the system. The time they spent was approximately from 1 to 2 minutes. Some participants discovered that utilizing numerous strokes to reinforce the contour was beneficial. In conclusion, this paper proposed a novel interactive cloud painting approach, generating authentic-looking clouds with fast sketches via C-guns. Using our method, users can paint volumetric clouds by sketching simple strokes on the canvas without confronting complicated workflows and setting the parameters in physical simulators. The user can quickly modify the result through later input sketches and erasers within minutes. The main contributions of this system are threefold: a novel approach to conveniently and interactively creating and editing volumetric cloud scenes from simple strokes, including drawing multiple layers, edge blurring, and erasing. It takes user sketches of simple and stochastic lines as input and infers sketches to approximate the contours of clouds and synthesize a corresponding image via C-guns. A representative method for editing painting particle system subjects in amorphous structures and translucence, without complex physical simulation and parameter setting. A dataset of volumetric clouds reserving the alpha channel to maintain characteristics such as density distribution, silver lining feature, and light flux. The dataset can also be a future reference for artworks and climate studies. The future work will focus on collecting more diverse and detailed data about volumetric clouds, improving the performance of the neural networks, and developing better detail and refined processes. Additionally, we will study how to optimize user experiences and empower the sketch-to-cloud transformation. We will also explore an extension system that can synthesize and edit volumetric clouds of 3-dimensional formats via our simplified sketch-to-cloud streamline. That's all, thank you.